All right, welcome back. So last time, we got our first look at the power of polynomial regression. But honestly, that was just scratching the surface. Today, we're going to really get under the hood. We're going to see exactly how it works, and then we're going to tackle the big challenge it brings up, how to control the model's variance. Okay, let's get into it.
So let's just start with the main puzzle, right? We know linear models at their core are designed to draw straight lines. That's what they do. But the real world, it's just not that simple. It is full of all kinds of curves and complex patterns. So the big question is, how can a tool that only gets straight lines possibly solve problems in a world that's fundamentally curvy?
You see, the problem is this. A basic linear regression model just assumes that the relationship between your inputs and your output is, well, linear. It's stuck with this straight line limit. So if the real pattern in your data is a curve, maybe a parabola, or something even wilder, a simple straight line is just never going to capture it properly. It's just a fundamental mismatch from the get-go.
But what if we could give our linear model a little superpower? What if we could let it bend the rules, just a bit, without completely breaking them? Well, that's exactly what polynomial feature transformation does. It is such a clever trick that lets our straight line model suddenly see and fit all those curves in our data.
And you know, the way this works is actually surprisingly simple. First, we just cook up a new, what we call a synthetic feature. We literally just take a feature we already have, let's call it x1, and create a new one by, say, squaring it. Then, step 2, we just add this new squared feature to our model. And here's the magic part. Step 3, the model itself is still linear. It doesn't change. It just thinks it has 2 input features now, and it learns a weight for each one. But because one of those features is just a powered-up version of the other, the final shape it can draw is a beautiful curve.
And you can see it plain as day right here. On the left, you've got your standard linear equation. That's a recipe for a straight line every time. But look at the right. After our little transformation, we've added that one crucial piece, the x1 squared term. That single addition is what gives the model the flexibility to bend and to form a curve that can really hug the data. We didn't change the algorithm at all. We just gave it a smarter feature to work with.
Okay, but all this newfound power, it comes with a pretty serious warning label. When you give your model this much flexibility, you're handing it a really powerful tool. And you can make it too flexible. If you do that, you'll fall right into a classic trap we call overfitting.
Now, to really get what overfitting is, we have to talk about model variance. The easiest way to think about variance is as a measure of a model's wiggliness, or maybe its instability. A model with high variance is super sensitive. If you show it a slightly different set of training data, its whole prediction can change, like dramatically. It's basically reacting to every tiny little fluctuation and all the random noise in the data.
So how do you spot this in the wild? Well, a high-variance overfit model, it looks like a genius on the data it trained on. It gets an A+, no problem. But the moment you show it some new data it's never seen before, it completely bombs. And why is that? It's because it never learned the real, underlying pattern. It just memorized the noise in that specific training set. It completely fails to generalize, which, is the entire reason we build models in the first place.
But here's the thing. This isn't some fundamental flaw. It's really just a tuning problem. The degree of the polynomial we choose, whether we square a feature or cube it or take it to the 10th power, that acts like a control knob for complexity. Our goal is to find that perfect setting. It's a real balancing act, dialing in just the right amount of flexibility. Let's just break this down. This table really shows the whole trade-off. If you go too simple with a low-degree polynomial, you get high bias. Your model is just too stiff and it completely misses the real trend. We call that underfitting. Now, if you crank the complexity way up, the exact opposite happens. Your variance goes through the roof. The model starts memorizing noise and can't generalize it all. That's overfitting. The goal, the sweet spot, is right there in the middle, a moderate complexity that gives us low bias and low variance. That's a model that's actually useful in the real world.
I absolutely love this analogy. Think of your model as a sculptor. If you only give them simple tools, like a low-degree polynomial, they can only make a rough, blocky shape. That's underfitting. But if you give them hyper-detailed, microscopic carving tools, a high-degree polynomial, they'll start carving every single pore and tiny flaw in the stone. You get a fragile sculpture that doesn't really capture the person's true form. That's overfitting. The whole goal is to give the sculptor just the right set of tools to capture the essential, smooth curves, while ignoring all the little random imperfections.
And that, of course, brings us to the big question. We get it.
We understand this push and pull between a model that's too simple and one that's way too complex. We know there's this fundamental trade-off between bias and variance. So how do we systematically find that perfect balance? How do we actually master this thing? Well, that is exactly what we are going to dive into in our next explainer. I'll see you there.